And good morning, good afternoon again. Peter Thomas from Control Specialists. This is a webinar on PROFINET Diagnostics. Right, okay, so by the way, if you have any questions, put them in the chat window. I'll address them at the end. If you've got any problems, again, use the chat window. So I am assuming that you can hear me clearly and you can see this screen. So here we go. So basically then, if you've been on this site before, then we're basically involved in the support, commissioning, and ongoing maintenance of industrial process control systems, and in particular nowadays the networks that interconnect them. And we've worked in a wide range of industries, but we also provide training courses, so certified Profibus engineer, Profinet engineer, and so on. And I've been to Australia several times to deliver these courses. So basically, as I mentioned before, the third webinar that we've given over the last couple of weeks, this is PROFINET Diagnostics. Next week, we've got one coming along for PROFINET Gateways. And then on the 1st of July, we changed the subject completely and go over to Profibus, and in particular look at lightning surge protection. This is being recorded, so we're going to be uploading it to our YouTube channel. There will be an opportunity for you to watch this again, and you will also receive a PDF copy of the presentation. If you're watching this at a later date when this is not live and you want a copy of the presentation, then just drop me an email. My email details are at the end of the webinar. Okay, so a brief reminder then, if this is your first time on the webinars, PROFINET, it's an example of what is called a real-time deterministic industrial Ethernet communications protocol. In other words, it's standard Ethernet running at 100 megabits per second, but whereas Ethernet is a best endeavors network, in other words, it will get through as quickly as it can, PROFINET is real time. It is guaranteed to get through at a given rate. It's designed or defined as being fast Ethernet, and it predominantly uses copper, but fiber and wireless are available. It's like its predecessor Profibus, primarily associated with the communications between PLCs, which we're going to call I/O controllers in the PROFINET world, and the plant-based devices like remote I/O, variable speed drives, pumps, etc., etc., but primarily designed for working in an industrial environment. PI, the international organization that's responsible for the technology, the marketing, the training associated with Profibus and PROFINET, keep a track on the number of devices out there. And this chart is showing that as of May last month, they reckon there was just over 30 million devices out there. If we compare this with Profibus, there's probably about 60 million devices, but that is starting to slow down. It's not falling, but it's certainly slowing down, whereas year on year, PROFINET is increasing. So it's definitely coming your way if you've not got PROFINET already. So this little diagram, again, you may have seen this on the previous ones. It's just to kind of instill into people that unlike Profibus, which is only going to be carrying Profibus traffic, a PROFINET system is likely to be carrying different types of traffic all on the same cable. There will be the conventional Ethernet traffic. Maybe somebody's got a laptop plugged into the network doing some diagnostics or accessing some web server on the site. There will be real-time traffic, which I'll explain the difference between real-time and also isochronous real-time. These are the time critical PROFINET communications. So basically you need to consider a PROFINET cable almost as being a multi-lane highway in which there are lots of different traffic all doing different things, certainly far more than just PLC to remote I/O communications. So to remind you then, in terms of the gear that we see on a PROFINET network, we're going to see at least one I/O controller, the PLC, in other words. In the Profibus world, we used to call this the master, but we call it an I/O controller in the PROFINET world. There could be more than one, but typically there is just the one. We have several I/O devices, the guys that the PLC or the I/O controller needs to communicate with. So we have remote I/O, drives, encoders, and so on and so on. We don't call these slaves, and the reason that we don't call them masters and slaves is that in the PROFINET world, the controllers and the devices sit at the same level. They are both enabled to initiate communications and not reliant on the other party. We then have the switches to join these guys all together. It is possible to have a PROFINET network without a switch, but there are issues about doing that and limitations. So we need to make sure that we've got the right kind of switch, because if we get this bit wrong, it can make our network very difficult to support moving forward. Then we have the gateways. Very often there is a need to link PROFINET to other PROFINET networks, or maybe to other types of networks like Profibus, ARSI, CAN, and maybe even a requirement to go to some higher level Ethernet-based IoT or industrial Internet of Things, where we're using protocols such as OPC UA and MQTT. That kind of traffic won't be controlled traffic, it will be traffic associated with data from the plant for some kind of higher level analysis. So we need to be aware of all of these things, and last week we talked about all of these and the importance and the role that they play. Then we have monitoring tools, and these are going to be seen as being essential to the qualification and support of the PROFINET networks, and this is predominantly what we're going to be talking about today. So last week we talked about the network design and the fact that if you've actually ever configured a PROFINET network, it's very, very simple, but it can lead you into a false sense of security, thinking that everything is fine. And the issue that we have is that a poorly designed network has the risk of underlying problems being there that you may not be aware of, and it can take several months, even years, for these things to come to the front. And in my experience, having been on many support calls, I've yet to have a support call on PROFINET that ends up being a physical issue. In other words, cabling or interference or reflections that are very common on Profibus. I've not had one. I have had many calls where people have had an uncontrolled mix of PROFINET devices and standard Ethernet devices. And whilst it's no problem at all linking the two together, if we do it to a point where we have too much Ethernet traffic, then the time criticality of the PROFINET system is at risk, and we then have network outages, and that's what we're trying to avoid. The main thing to remember here is that the PLC has got some basic diagnostics, if only visually in terms of an LED, a bus fault. If the bus fault LED comes on, it tells us that he is not communicating with one or more devices. However, the fact that the bus fault light is off is not necessarily an indication that the network has no problems whatsoever. We need to have a look at the underlying communications. And as we're going to see, a PLC is quite limited in that aspect. So this presentation is going to concentrate on the need to ensure that the network can be qualified against some kind of design during the commissioning stage, and that it lends itself for ongoing support moving forward. So what are we interested in then from a PROFINET Diagnostics point of view? Well, first of all, we're going to need to understand what the criteria is for qualifying a network. We then are going to look at the diagnostic capabilities of I/O controllers. Every PROFINET network will have at least one, so it's certainly worth having a look to see what they can tell us about the state of our network. We're then going to have a look at the switches and what they can tell us about their role in the network, because this might help us locate a particular problem. We're then going to have a look at dedicated PROFINET monitors, and we're going to see that these come in two forms. One is called an active diagnostic device, and the other is called a passive diagnostic device. They work very differently. They are very, very rarely, if at all, combined in one box. So sometimes we need to basically have two separate devices, or sometimes we can add to an existing device to give us the best of both worlds. We then can go to a very low level looking at Ethernet frame analyzers, which is free to download, so that's a positive. And then we're also going to have a look at, well, what equipment do we need to actually get on a network, especially if the network that we need to support doesn't currently have any diagnostic capability at all. And then finally, we'll have a look at the IIoT logging aspect of all of this. We're going to look in that in more detail next week, but we'll briefly mention it now. So, okay, so what is the quality criteria first of all? Well, basically, PI are the organization, as I mentioned, that control the technology, the marketing, the training, and there's an agreed set of criteria that defines a PROFINET network working at optimum levels. The first is that we don't want any dropouts. In other words, there should be no interruption to communication. Remember, I mentioned last week that one of the features in PROFINET is the ability to set the device polling rate on an individual basis. And in that respect, we need to have a knowledge of the process. So if, for example, one of the guys was being polled at 2 milliseconds, then by default, the watchdog of that device will be set to 3 times that polling rate. In other words, 6 milliseconds. As long as the PLC or the IO controller gets at least one of the 2 millisecond telegrams within that 6 millisecond period, he'll be happy. However, if we lose more than that, then we will have a dropout. So we want to make sure there are no dropouts. We want to make sure that there is no evidence of any telegrams being corrupted by maybe EMC, maybe cabling issues, etc. It would be useful to know. The PLC is not going to be able to tell us this kind of thing. Frame discards, these are basically a situation where a switch which has queues inside to store all of these ready for ongoing transmission, where it starts to become full, and eventually it has to discard some of the telegrams because it can't fit any more in. Well, that's usually an indication of network loading issues. So it would be very useful if we could poll the network to find out if any devices are dropping packets in this respect. Missing frames. When the PROFINET network is communicating, every telegram has a value, a counter value that increments in an integer. So for example, a 1 millisecond polling rate, this counter value increments in 32s. So the first one will be 32, the next one will be 64, 96, and so on. So if, for example, we've had the one that had 32 and the one that had 96, we can tell that a telegram is missing. We don't know where it's gone, but we can at least flag it up. And that is possibly an indication of network instability that we might want to look at. Again, the PLC is not able to tell us this. Jitter is a measure of how closely we are keeping to the agreed polling rate. So if, for example, we're on 2 milliseconds, then we wouldn't want to be any slower than 3 milliseconds, half of 2 being 1. So basically 50% we can accept. But any more than that, we want to start looking at the issues. And overall, our network should be designed such that normally we're only using about 20% of the bandwidth. This then facilitates the ability to deal with any short-term bursts due to large frames from Ethernet packets, and also for future expansion. So they are the criteria that ultimately will dictate whether or not the PROFINET network is working as required and within specification. So clearly we're going to need some equipment that can tell us whether we're meeting that criteria. So let's have a look then. We clearly have an IO controller, the PLC, and as time's gone by, these PLCs are becoming better and better at giving diagnostics. And some of them start just with a basic bus fault LED, no interaction with it. It's just an LED on the front, which will be illuminated when there is a bus fault, when he has lost communications with one or more devices, and generally will be off. Basically, though, accessing the diagnostics of these I/O controllers assumes the following. First of all, that the system integrator has decided to put them on some kind of operator panel, which isn't always the case, or that the I/O controller has got a built-in web server that has been configured to display these diagnostics, and more PLCs are now having these built-in web servers. That the I/O controller possibly has a built-in display to show these diagnostics. And you can see that the guy at the top, he's a Siemens S7-1500. He has got a small LCD panel that you would be able to interact with and see some basic diagnostics. Or you have a copy of the software and you're conversant with it. So there's a number of ways that we can access the diagnostics within a PLC. But this is the problem, that whilst the diagnostic capabilities of PLCs are very detailed, they generally only tell you about themselves and possibly diagnostics being generated by the remote I/O, the I/O devices. It's very limited when it comes to network specific diagnostics, and you're going to struggle to qualify your network based on the diagnostics that the PLCs can tell you alone. So where do we go next then? Well, okay, let's have a look at the switches. We mentioned last week that it is actually possible to have a PROFINET network without any switches at all, in that we can connect the PROFINET devices in a line similar to Profibus, where we go in and out on what we would call a daisy chain. However, when we're doing that, there are some limitations imposed on us. Will be what's called a line depth, that a maximum limit to the number of devices in series that's dependent on the polling rate. But also it becomes difficult to fault find in terms of pointing the finger at a particular device causing the problem. So switches are always useful to have, not only in terms of diagnostic capability, but also in terms of the availability of the network. And last week I mentioned the various topologies such as star, tree, and ring that were available. But basically, the more a network becomes segmented, then it becomes more and more difficult to determine the location of a fault unless the switch has got inbuilt diagnostics. And we can use unmanaged switches on a PROFINET network. There is nothing wrong in doing that as long as they support the quality of service protocol. However, if you do go down the route of using an unmanaged switch in a PROFINET network, you're going to severely limit your ability to qualify and support that network moving forward, primarily because unmanaged switches have no diagnostic capabilities whatsoever, apart from the LEDs that are flashing to say the port is working or it's not working. So basically, this is the issue with using unmanaged switches. So PI recommend that you use a switch that is classified as being a Conformance Class B managed switch. And the definition of a Conformance Class B switch is one that, first of all, is a managed switch. It's got a web interface. It can be configured via the web interface. It's got diagnostics, but it will also come with a GSDML file. And that means that the switch itself can be incorporated into the hardware configuration of the I/O controller, and it makes project management a lot easier. But we would consider a Conformance Class B switch as being the minimum requirement for use on PROFINET networks moving forward. However, if your role is there to try and save money, then basically you may be forced down the unmanaged switch route. So just be aware of it. Really, Conformance Class B is what you're looking at. All of the big manufacturers make these. Whether they formally define it as a Conformance Class B is another matter, but the easiest way to find out is if it comes with a GSDML file, it will almost certainly be a Conformance Class B switch. And fundamentally, from our point of view, we're interested in this because of the diagnostic capabilities from a PROFINET point of view. So basically, any Conformance Class B switch will have been certified by one of the 11 or 12 PI test labs around the world, and they're going to incorporate a web interface. They're going to come with a GSDML file, as I've mentioned, for incorporation into the hardware configuration. They will need to have a device name like the IO devices, and they will be allocated an IP address so that we can access the web server for configuration purposes. And as well as supporting the quality of service protocol, they're going to come with at least two very important protocols from a diagnostic point of view and support point of view. One is called SNMP, Simple Network Management Protocol, and one is called LLDP, Link Layer Discovery Protocol. And these combine to allow a number of features to be enabled within PROFINET. One useful feature is the ability, for example, for a replacement device to be automatically renamed without any software. That is very useful, and LLDP and SNMP play a part in that. But the biggest bonus of a Conformance Class B switch is the ability to have diagnostics specific to their individual ports. So in other words, it's going to allow us to localize a particular problem and get to the source of the problem a lot quicker. It also supports something called port mirroring, and port mirroring, which I'm going to discuss shortly, is basically the ability to either permanently or temporarily allocate a spare port for special purposes, where it will literally copy or mirror the traffic from one port to another for monitoring purposes. So that can be useful, but it also has limitations. And then we move on to the dedicated diagnostic tools. And they currently are either hardware or software or a combination of both that are specifically designed to monitor the low-level performance. These are the guys that are going to be able to tell you whether or not your network is operating within defined criteria. There's three main companies out there. There's Procentec from the Netherlands, Indersol from Germany, and Softing from Germany. All very, very similar in terms of what they do. And they do not form any part in the communications. You do not need to modify the hardware config or the software. If they fail, in other words, they lose power, then generally that will not affect the communications. There will be a make before break switching mechanism in there. And the purpose of these is that, first of all, they allow you to do the initial qualification of your network. So this is good for both sides of the fence. The system integrators that want to know that they're not going to be called back for problems that ultimately were nothing to do with them. And from the end user, they know that they can sign off this the invoice for this work, knowing that there aren't any underlying problems. And if you're going to keep these devices on the network permanently, they will also give you advance warning of any deterioration of the performance of the network before the network starts to visually cause problems. All of these guys are really designed to be permanently connected to the network. Because in that way we have this advance warning. But the reality is many companies don't do this. It wasn't included in the budget, etc., etc. So from a support point of view, we very often find ourselves going onto a network that has no diagnostic tools, and then these things basically become portable for just for the duration of the network support visit. As I mentioned earlier, these tools come in one of two forms. They are active and passive. Both of these are equally important. You would very rarely want to choose one over the other, and ideally you want to be using both to get a full picture of your network operation. So what are active analyzers? Well, the clue is in the name. They are basically actively polling the network for information. They are adding an extra load to the network, which normally should not be a problem anyway. And they're basically asking all of the devices and the switches, tell me about yourself. Give me your local diagnostics from a communications point of view. Now, that assumes that the devices and the switches can actually support the request in the first place. And one of the most common requests that active analyzers send out are SNMP GET requests. And if your switches and your devices don't support SNMP, then they will not be able to answer. And therefore, we are then substantially limited to the amount of information that the active diagnostic tool can give us. So be very, very careful before you start buying an active diagnostic tool. Check on the capabilities of your network and check that your switches are Conformance Class B switches, or at least support SNMP. As I mentioned there, these are generally polling with SNMP telegrams, and that fundamentally only works if they support SNMP. The way in which we connect an active analyzer is simply to a spare port on a switch. It doesn't matter which switch. It doesn't need to be a mirror port if you know what they are. It is just a spare port. You're generally only going to need one active analyzer per network, and he will give you the full picture. Some of these devices are now able to also display the diagnostics associated with a separate Profibus network. And if any of you are using Profibus, and in particular using the ProCentec Combrix, well then their Atlas PROFINET monitor has the ability of polling a Profibus Combrix unit to bring in Profibus diagnostics, which is quite a useful feature. And it also provides the permanent monitoring aspect. As I mentioned before, these are completely transparent to the I/O controller. There's no GSDML file. The I/O controller does not know he's there. He will not affect normal PROFINET communications. Then we come on to passive diagnostic tools. And again, the clue is in the name, in the fact that these passively monitor the network traffic. They are not dependent on the ability of the system to support any particular protocol. But they do insist that they are physically installed normally at the busiest point in the network, and the busiest point in the network is usually between the I/O controller and the first switch. So we have a bit of a problem there, that if we're supporting a network that has no diagnostic tools, the only way that we can incorporate a passive diagnostic tool is to literally break into the network, which by definition means shutting the network down while we do it. It only takes a few minutes, but it might not be possible. So we might be constrained. It's clearly better to think of this up front. And basically, as I've mentioned, they don't transmit anything. They're just passively monitoring the traffic that is going in the cable between the PLC and the first switch. These devices are going to be in series with the traffic. And this is the biggest issue, the fact that they have to be physically inserted there. But once they are inserted, again, completely transparent to the PLC. They have no GSDML file. They don't form any part in communication. And if they fail, then we will not lose communications with the rest of the network. They don't become a common point of failure. Some analyzers require a separate device, a tap, to allow them to connect to the network. Other devices have that tap built into them. You can see the guy at the bottom right here. This is the one from Indersol. He's got two monitoring ports, but he's also got two ports that basically allow this device to sit in series. The guy at the top, which is the ProCentec Atlas, is one where we would need a separate tap, and we would connect to that tap via a USB interface. I've got that one on our network here, and that's the one that I'm going to be showing you. So, okay, so if we haven't got any of these, and we want to really have a look low level, then we can save a lot of money by buying a free to download Ethernet frame analyzer called Wireshark. Wireshark is not specific to PROFINET. In fact, it's not specific to any Ethernet protocol. It just allows you to analyze the frames that you are monitoring at a particular point in the network. It will generally be needing to use a tap or a mirror port to access this, but it's very, very low level. You are looking at bits and bytes to determine whether the faults are there. And the current state of play is that most of the permanent monitoring devices will provide Wireshark files when they detect an event. So that's quite useful, because Wireshark on its own has no record on event capability, and these files can get quite large. So Wireshark is not only available as a standalone software for you to use independent of any device, but basically the PROFINET monitoring devices will actually create Wireshark files for you to diagnose offline. Okay. The way in which Wireshark, which is software, laptop-based software, is going to connect either via a mirror port or a tap to connect it to the network. As I've mentioned, they can't capture on events, so it's a matter of you pressing the start button and then hitting the stop when you have done all of your diagnostic, but they can end up being very, very large. Some analyzers I've mentioned save what's called a PCAP file that then allows you to open it offline. So what is this port mirroring? Well, if I go to a site where there are no diagnostic capabilities, then the first thing I'm going to want to do is, yes, I'd like to use an analyzer and plug it into a spare port, but I'd also like to do the passive analysis. So I'm going to be particularly interested in finding out whether or not the switches that are on that network have the ability to have one of their spare ports temporarily assigned as a mirror port. And this facility is generally provided by switches or managed switches, and it's a term used, it's sometimes called a span port, but a term used to copy the incoming and outgoing packets from the port that you're interested in onto this port for monitoring purposes. If we plug into a spare port, we will just see broadcast traffic. If we want to see traffic from a given port, we have to assign it, use a mirror port if we're going to use this particular facility. It's usually enabled via the web interface of the switch, hence the reason for needing a managed switch. And PCs and laptops that use frame analysis software like Wireshark can capture in that way. And I've done that many, many times. But there are several issues regarding the use of port mirroring. Number one, if you've not got a managed switch, you won't have the option. Number two, if you've got a managed switch and there are no spare ports, you can't set up port mirroring. Number three, you may have spare ports, but maybe it's not a site that you're used to and you haven't got the password to access the web interface. That can be a bit of a showstopper. But the biggest reason why you wouldn't want to rely on port mirroring is that the actual task of port mirroring from a switch point of view is a low priority. If a switch starts to become busy due to normal operation, he will push down the task of mirroring ports to a very low level. And so there is a possibility that we may lose packets at the monitoring port and therefore come to the wrong conclusion. Generally, port mirroring is fine, but from a design point of view, we shouldn't be relying on port mirroring. So we want to be looking at taps. And here's an example of a tap. It's basically a physical device. It's designed for installing at the point that you want to monitor in series with the cable. So you can see here we've got two Cat5, Cat6 cables here, and literally the one on the top might be the one from the IO controller, and the one on the bottom will be going to the switch where the IO controller would have originally connected to. In other words, this gets mounted literally in series. The USB port in this case is for connecting to a laptop if you're doing the analysis on a laptop, or via some kind of dedicated device. They're completely passive, no IP address, no configuration at all. And although they can be inserted anywhere in the network, normally we want it at the busiest point. And again, these devices are there for permanent installation, if at all possible. And this is basically then what we've got. This is what's called an aggregated tap, where the traffic incoming and outgoing is aggregated into a common stream for analysis via some other software or some other tool. The problem that we have with taps is that they can be quite expensive, especially if you've got a number of these devices. And what a lot of companies prefer to do then is, instead of buying a tap per network, they will have a tap per site, and then they will have a permanently mounted Ethernet access point. And it's the Ethernet access point that is permanently mounted. And then when we have a problem, we then plug our tap with the two cables into the monitor ports that you can see there. Again, the Ethernet access point, no configuration, completely passive. If it fails, there's no problem with communications. And there's a significant cost saving here. The only problem with going down this road is that you don't have the permanent aspect, because the Ethernet access point is not doing any recording at all. It is literally what it says. It is an access point only. Now, basically, what we're going to do is we've got both on our network. So basically, just before we look at the network, we also want to consider the possibility of there being IIoT, Industrial Internet of Things. We might want to log data going out to some other higher level system, Ethernet-based system. It generally tends to be information for process analysis to try and reduce downtime, improve productivity, etc., etc. But many of the PROFINET Diagnostic manufacturers are now offering the ability to connect to these higher level devices. And typically, they are using one of two protocols, OPC-UA and MQTT. OPC-UA has been around for some time and has certainly been involved in the industrial automation world. MQTT has tended to be more popular with home automation, but is now starting to show itself in the industrial automation world. And there's a lot of companies that are now providing these tools to allow you to send information up to some higher level system, either an edge server or a cloud-based server. So again, we might want to be looking at that in more detail. I'll briefly show you that on the tool that I'm using, and I'll be talking about these protocols and giving you a demonstration of MQTT in the industrial automation world next week. So before we move forward, we need some kind of qualification document to say what is it that we are going to test, and this should formally define all of the tests and include the criteria that we are wanting to test. And basically, somebody goes through the test, and this is your formal evidence that there are no underlying faults. Far more than just saying there were no bus faults, therefore the network must be working. So this is our network. We have two I/O controllers. This controller here, I/O controller 1, is going to control the devices in racks 1, 2, and 3 over here on the right. I/O controller 2, completely dependent device, is controlling the devices in racks 4, 5, and 6. We have a number of switches to connect them, and we've also got an office switch, which forms no part in the PROFINET communications. This network also has diagnostic capabilities. So let's have a look at how we would initially join these up. We've got an operator panel on here as well. We've got some local PCs that may be permanent or temporary. And basically, we're starting to add these devices, build the network up with copper or fiber. And we've got some gateways that we're going to have a look at next week. So this is basically our network without any diagnostic capabilities other than those provided by the controller and the switch. If we want remote access, we can then bring this in via a separate route, and I'll be showing you that next week. What I'm interested in, though, is the aspects or the ability to start looking at some diagnostics. So I'm just gradually building our network up to a level of complexity, but we've got no dedicated monitoring devices on here. And this is what we're going to have. We've got a separate PROFINET monitor, an Atlas from Procentec. He is by default an active diagnostic tool, so we're going to connect him to port 6 of our switch, a spare port, but he's also got the ability of being extended to become a passive tool if we add an ether tap. Now that ether tap really should be in series between IO controller 1 and port 1 of the switch, or IO controller 2 and port 2 of the switch. In other words, we really need 2 taps. What we've opted for is to buy 1 tap, and then we're using these permanently connected Ethernet access points. So what we will do is we will plug the tap into the top one or the bottom one, depending on whether or not we want to access or monitor controller 1 traffic or controller 2 traffic. So let's give you some demonstrations then. What I have on my network here is all done from a web-based interface. So all that I'm doing is I'm sat with a laptop plugged into the network, and the first thing I've done is I've typed the IP address of the PLC. And the PLC, even though this is only a small S7-1200, has got inbuilt web server, and it has things like diagnostics in here that we can have a look at. This basically has the ability to expose additional information. So we have diagnostics about itself in terms of its memory. We can basically have a look at the diagnostic buffer within the PLC. So we don't need the programming software to do this. This is all basically shown here for us. We can have a look at the modules. We can look at the communication in terms of its view of communication from a local point of view, not the network as a whole, but whether or not he's having any issues at his particular port. And you can see here, are there any errors, and so on and so on. But this is very much localized at the PLC. If you're a Siemens user, you might be interested in knowing that the watch tables that you can create within the software, you can actually expose them to the web interface so that you can allow people to have a look. So I've basically created one here showing me some flags within the PLC, and these numbers update. It's a slow update, 10 seconds, so you're not going to see numbers whizzing around. The bottom line is the PLC has a limit on showing you detailed information about the network. So let's have a look at the switches then. Here is a switch, one of the switches on the network. This happens to be a Siemens Scalent switch. And this switch has basically got a number of things that we can change from a configuration point of view. But if I click down here on statistics, we'll see various things that we can have a look at from a localized point of view. And in particular, we can look at packet errors. And he's telling us things like, on port 1, are there any framing errors, cyclic redundancy check errors, CRC, corruption, undersize, oversize, all sorts of problems. There are clearly none here. So this would have the advantage that if we had a problem, we could look at a switch, knowing where it is, and find out what the problems are. We're not limited to Siemens. We can go on to other switches. So on here, we've got a switch via a company called Ingersoll. Let's have a look at this one. A fresher interface. This is quite nice because we can basically look at the ports and see if there are any issues from a different criteria. This one is clearly telling me that port 1 and 3, they're working, but they're not the right devices connected to the port. In other words, the actual topology is mismatch between the design topology. We can have a look to see if what the load is at that point in terms of, you can see on here, different issues from a loading point of view. We can look at discards. In other words, have any of these ports had any problems with discards? And the answer is no. All of them are 0. Are there any errors? Purely from this port, this particular network device's point of view, not the network as a whole. And then finally, we can then go on to a PROFINET diagnostic tool. And this is the Atlas, the permanent monitor. This is basically then going to permanently monitor the traffic. I can go along. I can first of all ask it to build a topology. It can take a few seconds to do so, but once it does this, it then gives us a view of how everything is interconnected with one another. You can see on here, and we are able to zoom in on here, and if we want to move things around, we can do this. And if we double click on any of these guys, it will tell us a little bit about itself in terms of where we stand, what kind of device it is, and so on, and local issues in terms of the port loading on its in and out port. So just a click of a button. If I go back to the dashboard, I have an alternative way. I can look at what they call the Q factor. And the Q factor is a high level measurement of the communications performance of each device on a PROFINET point of view. And if I click on any of these for this guy here, this is the criteria. So it's telling us literally what, whether there have been any errors, any loss, what the loading is. Remember, we're looking at less than 20%, and so on. This is my laptop here, so we're not going to get much information from there, but just a high-level overview of how the devices are operating from a communication point of view. If I want to look at the events, I can have a look here, and it will tell me basically, when I click, it will tell me on here what information, what issues he's seen. So he's seen some devices dropping packets. We've not lost communication though. The PLC has never lost communication, and we might want to have a look at what's causing this problem. It might not necessarily be a PROFINET problem. We can have a look at the device list, and in particular, whether there are any high-level issues associated with the devices that have been detected, what the load is through these devices, making sure that they're less than 20%. And also, you will also see, wherever it's been possible, the firmware. And you can see these two devices, he's flagged up as being a warning that we've got two devices on the network that are the same, but they're operating at different firmware. That may be a pointer to a problem that we have. If I move on, I can going back to the dashboard, I can go down here. We'll show you the report shortly. I can also go on to the EtherTap device, and this is the diagnostics specifically coming from the tap. And if I click on this guy, this is additional diagnostics at the busiest point in the network. And what he's able to tell me is, in the cycle time, this is actually the configured cycle time, and the jitter is the variability around that in percentage. And we don't want a jitter of more than 50%. And you can see this is happening fine on here. But we've also seen he's seeing drop packets. Drop packets aren't necessarily an indication we've lost communication. We would have to have a large number of them in a sequence for this to take place. So this is a very brief overview of it. What I'm wanting to show you is the level of detail we can go to. I have the ability to set up MQTT here if I want, and I'll be showing you this next week. But also what I can do is there is the option of a report, and I created this report earlier, and this is the report that we can use as evidence of having qualified our network. I wouldn't suggest that this is the only report. You might want to do a bit of writing around it to say that you have actually looked at it and that you're happy with it, but it's quite detailed, and it's certainly a good way of looking at the your particular network. But that basically brings us to the end of this webinar. It's been a quite quick. It's not a training course. We can go into it in a lot more detail than we have, but the purpose being just to have an idea of the importance of making sure that your network can be supported and qualified. I've lost count of the number of times where in reality a network has gone in where they have passed all of their tests in terms of the normal operation of the network, but nobody has had a look at underneath, and ultimately the network is operating on the cliff edge. It could fail, but it hasn't failed so far. So that basically brings us to an end. If you've got any questions, now is the time. You can put them in the chat. If not, and you think of any questions later on, then just give me a shout, drop me an email, or contact me on LinkedIn. I'll be contacting you with, if you're watching this live, I'll be sending this to you via PDF, and the PAA will send you a link to this for watching at another time. But apart from that, that is it. Hope it's been of some use to you and that you can make use of the information in your job. Thank you very much for your time, and I will speak to you again. Thank you very much.